Hello, welcome to the webinar Advancements in Area Velocity Flow Measurement, brought to you by Electronic Data Solutions. In our webinar today, we'll have a brief introduction to area velocity flow measurement, then we'll watch a short video, and then we'll go into the measurement technology that's being used by the ISCO laser flow sensor. We'll talk about mounting hardware and techniques for the sensor, and then we'll explore some applications, especially highlighting previously difficult to measure applications. So with that, we'll get started. Electronic Data Solutions is bringing you the webinar today. We've been in business for over 29 years, specializing in water resource instrumentation, mobile field computing, and field data collection instrumentation. We offer a variety of hardware and software solutions, complete with technical support, training, and repair services. Our main office is in the south central town of Jerome, Idaho, where we have 25 employees in the company, and we have 5 remote field offices. I'm talking to you today from our satellite field office in Ogden, Utah. Before we get started talking about advancements in non-contacting area velocity flow meters, I think it would be a good refresher to talk about the flow calculation commonly used. Q, which represents flow, equals A times V, where A is equal to area, and with an area velocity flow meter, we actually get our area from the pressure or ultrasonic sensor measurement. So we measure the water level with either one of these two sensors, and then we multiply that level with the cross-sectional geometry that the user would have told the flow meter what they were using. For example, if you had a 36-inch round pipe, you would tell the flow meter what you have. It would measure the depth in that pipe, multiply those two values together, and get the area component in this equation. Next, we need to get our velocity. We can measure our velocity with a Doppler sensor, either a submerged contacting sensor or a non-contacting sensor. So simply by measuring the velocity with one of these technologies, multiplying it by the area, we get our flow measurement. With our submerged probe area velocity sensors that we've had out for some time, the sensor is mounted in the bottom of the pipe using some type of stainless steel mounting band. There's a pressure sensor at the bottom of this probe that measures the water level on top of it. And just like in our equation, that water level is multiplied by the geometry and the dimensions of the channel to get the area. And then sound waves are reflected out of the, sound waves are sent out of the beveled front end of this sensor, and we get reflection that comes back based on particles that are entrained in the water column, so we can find out how fast that water is moving, giving us our water velocity. And again, those two values are multiplied together to get the flow rate. For much larger pipes, we take a more sophisticated approach with the Doppler area velocity flow meter, and we use what's called a time-gated or pulsed area velocity flow meter. Again, we have a bottom-mounted, or in some situations a side-mounted sensor, but in this case we're actually putting the sensor in a pulse coherent mode where we can actually profile throughout the whole water column. So this allows us to achieve much greater flow accuracies in large pipes. So if you look at this diagram in front of us, these yellow lines that look like a reed in the water, each one of these represents a bin or a cell where a velocity measurement is taken. And these sensors have these bins are sent out on different angles to try and capitalize on as much of that pipe or channel geometry as possible. So we can essentially know what the water velocity is from the bottom all the way to the top of that channel or all the way to the side of the channel. And then the depth is measured with an up-looking ultrasonic sensor. So by using these components, we can accurately measure the flow rate in much larger channels, be they round pipes, trapezoidal ditches, rectangular channels, whatever you have. And by doing this, we can get these kinds of pictures where we can actually see that velocity structure, that velocity profile within the pipe as depicted by the graph in the lower left-hand corner. But at the end of the day, any submerged probe that you have in the bottom of a channel may be subject to some degree of fouling, either by sediments, by debris coming down the channel. In the case of wastewater collection systems, they call this ragging, where you have a lot of materials within a raw sewer environment that can build up on those pipes. Now, in these situations, these sensors can still give you an accurate depth reading, but if all of the sensor faces are blocked, you're not going to get a velocity reading either from the continuous wave Doppler sensors nor from the time-gated pulse sensors. Now, in those meters, we do have some technology or some features to deal with that we call flow rate 2, where basically you can have the flow rate based on the Manning equation. Even if you don't know the slope or roughness coefficients of the channel, we can use some features in our FlowLink software. So if you've captured a number of days or weeks worth of good data with a clean sensor using the area velocity sensors, we can basically superimpose those graphs on top of each other, and it will set the slope and roughness coefficients for you. And then from then on out, when the sensor becomes covered up, it'll use that those variables to calculate flow based on the Manning equation. However, if your channel dimensions are suited for it, there is a better way, and that's actually removing the sensors up out of the water altogether and having the measurements taken that way. So with that, let's listen to and watch this short video, and then we'll look at some additional slides. So the market need drove the advancement of non-contacting measurement for more accurate data than basic ultrasonic sensor using the Manning formula, which the literature says can have an accuracy of plus or minus 20% or worse, and there was no way to handle surcharge or submerged flow conditions. So we want a technology that meets or exceeds contact area velocity sensors in all of these areas. Okay, that was great, and I think gave us a good introduction to this sensor that we're going to be talking about. So now we want to look at the theory of operation in a little more detail with this specific sensor and discuss exactly how it works. One thing that the video didn't mention is another unique feature of this sensor is that we have the ability to face or position the sensor upstream looking into the flow or looking downstream into the flow. So that really gives you a lot more flexibility, because a lot of times in some situations it's really, you may not have a good read looking upstream where you have a lot better channel profile looking downstream with it. So this is kind of what was described in that video and how things work with the subsurface velocity measurement. So the frequency, so the velocity of the water is determined by a frequency shift between the transmitted frequency, which indicates the flow direction, and the magnitude of the shift, which indicates the velocity. Now, one thing to pay particular attention with in here is that it is, even though we're using light, it is still a Doppler sensor. So we actually need to have some particles entrained in the water. It doesn't need to be very much. Raw water works just fine. And obviously wastewater would be great too, but you may not get a good signal return if you're working in water like spring flow situations. See if we can get our slide to advance here. So let's talk a little bit about how the sensor is mounted and look at some schematics of the sensor. The range of the sensor, which is determined by the range of the ultrasonic depth sensor, is 0 to 10 feet. Because there is no deadband with the ultrasonic level sensor, as was shown in the video, the sensor can actually operate with the water right at or touching the face of the sensor, because ISCO has actually mounted the ultrasonic level sensor up high in the back of the sensor with a reflector plate or deflector plate at 22.5 degrees. So the sensor fires, hits that plate, and then goes down to the bottom of the channel, and this eliminates typical dead bands that you see in most ultrasonic level sensors. For the installation requirements, this is showing the sensor pointing upstream into the flow measurement. On permanent locations, ISCO offers the stainless steel mounting brackets that can be concrete drilled to the side of a manhole or any type of structure over the channel. The laser, as we mentioned, the laser can also be installed facing in the downstream pipe as well. You just center the bracket over the flow stream and away you go. Here's a picture of the stainless steel mounting bracket showing the mounting tabs, which help align it, especially if you're lowering the sensor in from the street level. This unique bracketry allows you to level the sensor using the bracket right and left, as well as for pitch and for roll. Here's another schematic of the mounting bracket. Every sensor has a bubble type level fixture on top of it, so you can do your coarse level adjustments with that. In addition to that, every laser flow sensor has an accelerometer inside of it, similar to your cell phone. So it will actually measure and record the pitch and roll of the sensor, and it outputs the data to your screen. So as you're doing your level adjustments, if you're doing it from up on the surface and can't see this bubble level, you can actually see the pitch and roll on your computer screen or on the LCD of the meter. Some more close-up views of that. This handle that's right there is shown, allows you to lock the laser flow in place on the stainless steel mounting bracket. So if there's any vibrations or issues with that, it doesn't float free or come free of that bracket. We also have a laser on feature, so once the sensor is positioned in the flow stream, if you want to see immediately where that laser focus is hitting, either through the keypad and LCD on the meter or through your laptop screen, you can toggle the laser on feature on and off to see exactly where it's going to be measuring. There's also a nifty street level installation tool available for the laser flow. So if you're somebody that goes to sites on a regular basis, you can mount these brackets in the column of the manhole, and then if you come by on a say a quarterly or a semi-annual basis, you can just lower the laser flow in, put it on that bracket, then give that pull a twist, lock it in place, release it, and then pull it up out of the manhole. So this gives you a good idea of how that works, how the installation tabs work, and the fact that you can work from a maximum of 23 feet from the surface. Now the laser flow is commonly used for temporary applications as well. For those, we have a ratcheting spreader bar that spans the column of the manhole or the channel. So you put that down in there, ratchet that in place, it pins that bracket to the sides of the channel, and then it uses a similar stainless steel mounting bracket that we use in our permanent locations. What we're going to highlight now are some previously difficult to measure situations with submerged probe type of area velocity flow meters, and just how you can make your non-contacting device work in these difficult situations. First of all is outfalls where you have a free drop. In these situations, you can order the ISCO laser flow with a remote ultrasonic sensor. So you would mount the sensor just like you typically would, except for the ultrasonic is now cabled to the laser flow, and we have these mounting brackets with these stainless steel bands that you would push inside of there. So we're measuring the velocity and the water level at the same location. You can see from the diagram here that it would be impossibly inaccurate would be the best way to put it, to actually measure the water level from the standard rear-mounted portion of the laser flow. So this option shows the remote ultrasonic level sensor accessory. So it allows you to adapt for the elevated discharge. Here's a real-life picture of that, where we actually have a drop out of the manhole, so you can see the water level is actually flowing from right to left. You can see a little lip right here where it drops, and then there's also a side channel, so the level under the laser flow is lower than the focus point, and it can also be influenced by this inlet pipe that would give you an artificially high reading as well. So this picture is showing the remote ultrasonic level, and let me see if I can grab my pointer here and draw that. So this shows it cabled right here, and there's a band up into this pipe further there where that sensor is installed. So again, what would have been a previously difficult to measure situation, with that with the remote ultrasonic sensor, it makes that much easier. And now I find I have to get rid of that and go back to my normal mode here to advance the slide. And just showing some data from that particular site. Another application that's always been difficult for submerged probe area velocity sensors are really slow velocity applications, or ones with really low water level. So there's a kind of a trifecta of bad things happening here. One, either low velocity, abnormally high velocity, and low water levels. And we can look at some testing that was done with this. We actually can measure to 1/2 inch minimum depth effectively and accurately with a laser flow. Now, typically with people that are working with our submerged probe area velocity flow meters, I like to see at least a minimum of 2 inches of water to get a good Doppler signal off of those. The sensor will give a reading with as low as a 1 inch of water, because the sensor itself is actually 3/4 of an inch. So again, not having a sensor in the water, even if the water is fairly clean and fouling isn't an issue, can be a big advantage if you frequently experience low water levels. And here's some comparison data showing again low water levels down to 1/2 inch, and we're seeing nice good diurnal fluctuations without a lot of noise even at those low levels. And velocities down to about 0.26 feet per second. The spec on the laser flow, we actually have it spec'd at. We like to see minimum flows of at least a half a foot per second, but we've seen a lot of good data at down around 0.25 or 0.26, and in this case flow rates as low as 3.99 gallons per minute. So again, you can see the red line in this middle pane, which is put there by our FlowLink software at this cutoff point of 0.5 feet per second, and you're seeing that almost half of the data is measured below that, and the client's still seeing very accurate flow measurements at those numbers. And again, some more low-level flow measurement data with the laser flow. In this case, probably 90% of the data is within a half an inch and 1 inch of water level, and we're still accurately tracking to 4 gallons per minute compared to a metering insert, which was typically previous to the laser flow was one of the only things that we could use to measure low water levels or low flows, specifically in manhole situations. So they'd have to push these flow metering inserts up into the pipe. There was a round rubber bladder around those things that you'd inflate with a foot pump that would seal that off, essentially creating a weir type of environment inside that pipe. Then we just use a bubbler water level system to measure the water level behind that weir. Now we can do that much more effectively, and especially for a lot longer term with the laser flow non-contacting system. Another condition that has always been really challenging was a steep slope, high velocity systems, and or a combination of high velocity and low water levels. So you can see in this picture here that water level is just really cooking in the bottom of this manhole. What would typically happen when you'd put submerged probe area velocity sensors in these situations, especially low level? Again, low level combined with high velocity, you'd get this type of rooster tail effect. So this is a close-up picture of Visco's low diameter, low profile area velocity flow sensor. This is a close-up picture of it because keep in mind the sensor that you're looking at is only 3/4 of an inch tall. But this is in a plexiglass flow chamber in a hydraulics lab at a local university here, which gave them the ability to easily adjust the slope of the sensor and how much water was coming down that. So this is what you'd be looking at if you were able to actually see your sensor in the pipe in high velocities and with something like 1.5 inch of water coming down at it. The effect is twofold. One, the water rooster tails off the front of this, so at this beveled front end where your velocity measurements are being made, because you have a sending and a receiving sensor in the front of this thing, you get some really erratic data. And then the other effect that you typically see is you get some really noisy water level data because there's a pressure sensor in the back end of this probe right here, and it creates some artificial or false pressures on this sensor because of this rooster tail effect. So again, by moving the sensor up out of the water, we can get a lot more accurate data. So again, this is showing another graph showing the middle pane. In the green here is showing the high velocity data. So the velocities are typically ranging from about 4.5 feet per second up to about 7.5 feet per second maximum. And you're still seeing these nice smooth diurnal fluctuations with this sensor. And this is something, especially at a low water level. I mean, look at the bottom of the blue graph and the upper pane right there, is we have water levels that are frequently below 2 inches. So again, with submerged probes, this can really cause some noisy or erratic data, and it's handled very nicely by the laser flow. One of the most accurate meters in a closed pipe situations are have been shown to be magnetic flow meters, so we took advantage of that with a downstream mag meter that was on a full pipe environment to capture or compare the data against the ISCO laser flow. So you can see in the bottom pane right here that we're getting pretty good comparison accuracy between the mag meter and the ISCO laser flow. This graph here shows the ISCO laser flow versus one of our ADFMs, which is simply an acronym for acoustic Doppler flow meter. Now the reason we are comparing it with the ADFM and are so happy with the accuracy data that we're seeing is that these ADFMs have been tested by a number of third-party hydraulic labs, federal government and university, and we've been able to see 1 or 2% accuracies with these ADFMs. There's just been always two things that have kind of slowed the sales of these. One is they can be tremendously expensive, typically between the $15,000 and $23,000 price range, and the other thing is that they have all of the failings of any submerged probe area velocity sensor that you're going to install, and that is that they can be subject to fouling depending on the environment that they're putting in. So we were really happy to see this with a sensor system that's roughly just a little more than half the price of an ADFM and has the advantages of being a non-contacting system. The other thing that we've done a lot of testing with is just repeatability of the data, installing laser flows side by side or in tandem on a stream, one facing upstream and one facing downstream an environment, and looking at with the flow rate right here how nicely they tracked right along with each other. ISCO offers the laser flow sensor with two of its meter platforms, either the 2160 module or the signature flow meter. For portable installations, and I'm going to clarify this by saying long-term portable installations, I try to steer people towards the 2160. It's powered by two 6-volt alkaline, what are called the lantern-style batteries. So if you drew a line right across here, the whole bottom part of this is the battery case. You have a door here and here that are sealed with rubber gaskets. You open those up and there's a lantern battery in each one. So we can typically get some really long battery life with these systems. So if you're leaving the meter out there and don't want to touch it with the ISCO laser flow sensor, no less than once every 3 months, then the 2160 is a good system to go with. You can also do redundant in-pipe flow measurement with the 2150 submerged probe. If you needed to go longer than that 3.5 month period, you can actually stack another battery pack. This is a modular system, so another battery pack would lock in right on the base of this, which would essentially double the life of your battery out in the field. So that's the 2160. It's just like our long-running and popular 2100 series module family. As we mentioned, we can also go with the signature flow meter. So we have really power-efficient electronics with this system. All of our flow meters have the ability for variable rate data storage. So if you have a system where you're that's typically pretty flat, but you want to capture storm events or industrial discharge releases, you can set up a primary data storage interval, say like every 10 minutes, and then you can put a rate of change or a threshold in there for any measurable parameter. And if the meter sees that, it'll automatically switch over to that faster logging rate to capture that flow curve in a lot higher resolution. There's a number of interface and communication options, including cellular modems, spread spectrum radios, snap-on displays, and of course, like all ISCO products, it uses our FlowLink 5.1 software for interfacing with it. Now, for either permanent or semi-portable applications, we have the Signature Series flow meter. The signature can be powered either by AC or 12-volt DC. It has a display and keypad on it. It has multiple and simultaneous inputs and outputs. We'll show a graphic of that in just a minute here. And there's a lot of field upgradable options on that. You have a USB flash drive interface, so anybody can walk up, plug in a USB flash drive, a display automatically pops up on the window where the user can select pre-programmed report intervals or just a download of all of the data. It also has variable rate data storage, just like the 2100 series, and there's cell phone and Ethernet communication options for it as well. It's also FlowLink compatible. However, a user can do all of the setup directly through the keypad and display on the unit, as well as data retrieval to a flash drive. Up close look of the signature meter showing the LCD and the keypad, and then showing you all of the number of options, inputs and outputs that are available with the Signature Series meter. So you can bring Modbus input in from some sensors, SDI-12. We offer it with a bubbler level sensor, an ultrasonic. We can provide a pressure transducer. The ISCO laser flow is certainly compatible with it. We can trigger automatic samplers, interface pH and temperature sensors, tipping bucket rain gauges, as well as we can also output Modbus 4 to 20 milliamp. You can get it with an Ethernet modem, USB interface, cellular modem in there. So lots of ways you can build this up. One of the nice advantages of this is for people that are measuring multiple locations from one meter or who want redundant measurement, is you can have multiple sensors connected to one signature meter at the same time. So in summary, the laser flow gives you advanced laser velocity measurement with the unique feature of having a subsurface multi-point velocity measurement. So it's the only non-contacting flow measurement system on the market that reads below the surface. It's precise and accurate because it's non-contacting. It's easy to install and maintain. It's better than submerged flow measurement option, and it's a flexible platform, either with the 2100 series or the signature meter that you can build on. Lastly, I just want to remind you of all of the water resource markets that are served by Electronic Data Solutions. We represent in situ for water level and water quality instrumentation, INW for pressure transducers, of course Teledyne ISCO water samplers and flow meters, and a sister company to Teledyne ISCO called Teledyne RD Instruments, acoustic Doppler current profilers. An example is shown in the upper right-hand corner with the portable Stream Pro ADCP. We also represent Hydrological Services of America, which makes a lot of tools for hydrologists, including weighting rods, price AA meters, tipping bucket rain gauges, shaft encoders, bubblers, things like this. And for pipe flow measurement, EMCO, telemetry and data loggers from Campbell Scientific, and we also do system integration services for people that want somebody to come in and install a whole package with telemetry. Also want to remind everyone of our GPS and GIS market served by Electronic Data Solutions. We are a dealer for Trimble navigation, mapping, and GIS type of global positioning systems for utility field solutions, environmental, and forestry. We're an Esri business partner developer. In fact, we are a Esri Gold partner for all the work that we've done with their software, and we also carry laser rangefinders, GPS-ready digital cameras, rugged tablets for mobile demand, as well as Juniper Systems rugged field computers and GPS bundles. We are an MGIS priority support partner for Trimble. We have 5 full-time resources on staff to provide training and support. We're a GPS GIS cooperative support for other companies as well. And we have a very extensive equipment rentals fleet for mobile field computing, either with or without GPS, and have an online store, an eBay store, as well as providing in-house sales and support. Again, I'd like to thank you all for attending today. That completes our recorded webinar of the Teledyne ISCO laser flow and this webinar presentation, Advancements in Non-Contact Flow Metering Technology. If you have any questions or need additional information, I invite you to contact our company. You can email me directly at steve@electdata.com, give me a call on my phone number, or visit our website www.electdata.com and access our products that way. Again, thank you very much for attending, and we hope to see you again on some additional electronic data solutions webinars.